Good evening, everyone. Welcome to my talk. I'm a third-year engineering student at the University of Cape Town. I'm the chairperson of the UCT Space Society, and I'm also the co-executive director of the South African Space Design Competition. In today's talk, I'll be taking you on a journey. We're going to start at Earth, and we're going to culminate at the edge of the observable universe. We're going to take this trip in stages. Each stage, an order of magnitude larger than the previous. And in each stage, we're going to encounter new challenges and new physics that we have to overcome to be able to traverse the given distances over the given periods of time. We're going to start off at Earth. We're going to look at how to get to the moon. We're going to look at how to get to interplanetary space and explore the entire solar system. From there, we're going to go interstellar and explore our local cluster, from which we will continue zooming out until we get to intergalactic space. And then we will continue zooming out until we reach the absolute edge of the observable universe. But to explore the universe at such a grand scale, it is very important that we start at Earth. So, before a rocket even gets off the launch pad, there's a very important criteria that needs to be met. This criteria is the thrust-to-weight ratio. The thrust-to-weight ratio is essentially just the thrust divided by the gravitational force acting on our rocket, and if our TWR is less than 1, our rocket will just stay on the launch pad, or if it's in the air, it's going to fall down or accelerate downwards. If TWR is exactly equals to 1, we're just going to be hovering in the air, wasting fuel and doing no useful work. If TWR is greater than 1, then our rocket will finally get off the launch pad and into the air. Normal rockets keep their TWR between 1.2 and 1.5. What's the reason for that? TWR of 1 will lead to you hovering in the air, and this is called gravity drag. Essentially, our fuel is being wasted to fight gravity, but we're not really accelerating towards space. But if our TWR is too high, then we're going to encounter a lot of atmospheric resistance because we'll accelerate too quickly whilst we're still in the lower part of the atmosphere. So we want to find a balance between gravity drag and atmospheric drag to minimize both of them so that we can find the most efficient way to get to space. So to choose an optimal TWR, we got to choose optimal engines. We can't really change the weight of a rocket much, but the engines we choose will decide what the TWR will be. It is important to note that a launch vehicle or a rocket has a different TWR to an engine. An engine has its own weight, and its TWR is much higher than a rocket's TWR, which will usually float between 1 to 2. Engine TWR is a measure of the sheer force the engine can create, the sheer upwards thrust it can create. But we need another metric to talk about fuel economy. This metric is called the specific impulse, or the ISP. This is essentially the number of seconds that 1 pound of propellant can produce 1 pound of thrust. So an engine with a low ISP but a high TWR is like a sports car, which isn't very fuel efficient, but it's extremely powerful. These engines are useful to get us from the ground into orbit. Then we have engines on the other end of the spectrum, which have high specific impulse but low TWR. So these are like your everyday commuter cars. And these are very useful once you're in orbit, and fuel economy matters a lot more than fighting a lot of gravity. So, like I said, different engines provide different combinations of these two specific quantities, and they're obviously useful for different parts of spaceflight. Now, what kind of engines can we choose? What are our options? Well, there's a bunch of options. The first option is a solid rocket booster. This is one of the best forms of propulsion to get you off the ground because it is literally just a booster. It overclocks your TWR when you're on the ground. It provides insane amounts of force, but obviously is not very efficient. So its maximum thrust is 14.7 million newtons of force that it's applying to the rocket. It's called a solid rocket booster because its fuel is solid. It's aluminium and ammonium perchlorate. And it's got a vacuum ISP of 268 seconds. The reason we're saying vacuum specific impulse is because we're measuring it without the presence of the Earth's atmosphere. Solid rocket boosters do have their own disadvantages. Once you turn them on, you can't turn them off until they're fully burnt out. You cannot control the throttle, so it'll burn at 100% at full power for the entire duration of its burn. But, like I said, they're extremely powerful and they're very useful for producing a lot of thrust on the ground. Moving on, we have the engine that took our Apollo astronauts to the moon. This is the Rocketdyne F1 engine, and a bunch of these were featured on the Saturn V rocket. Now, obviously, it doesn't have the thrust of the solid rocket booster. This one only clocks in at 6.77 million newtons. However, it's got a higher ISP, a specific impulse, at 304 seconds. All the engines from here on out are liquid fuel engines. They don't use solid fuel, they use liquid fuel. In this case, it's kerosene and liquid oxygen, shortened to kerolox. Now, kerosene is incredibly dense and stable at room temperature and pressure, which is why these turbopumps can dump a lot of fuel into the combustion chamber and get a lot of thrust out of it. This engine is based on an older design called the open cycle design, which isn't very efficient because it essentially dumps its exhaust overboard, as opposed to using it in the combustion process, as we'll see with later engines. However, like I said, this engine is what got us to the moon. Moving on to another form of a kerolox engine, we have the SpaceX Merlin 1D engine. This is a lighter engine, which means it is physically lighter, but it also produces less thrust. So it's got similar ISP numbers. This one is at 311 seconds. However, its thrust is only 981,000 newtons. It's used in the Falcon 9 and Falcon Heavy, and it follows similar design principles to the Rocketdyne F1, this is an open cycle, and like I mentioned, it is a kerolox engine. However, this is the highest engine TWR in orbital launch history, which means even though it doesn't produce a lot of thrust, it is so light that it can lift up to 200 times its own weight. Moving on, we've got the Rocketdyne RS-25 engine. This is another historical engine because this powered both the Space Shuttle missions and the Artemis missions. 4 of these are found on the core stage of the Space Launch System, and this is a fairly efficient engine because its ISP is 452 seconds and it produces 2.2 million newtons of thrust. This is not a kerolox engine, it is a hydrolox engine, which means it uses liquid oxygen and hydrogen to produce thrust. And like I said, this engine is extremely efficient, so if you pair this with your solid rocket boosters, you can get a lot of thrust whilst preserving fuel economy. The problem with this engine is hydrogen is not very dense, so the turbopumps that essentially pump fuel from the tank into the engine have to be very, very powerful, on the order of 10 to the 7 horsepower, to actually generate the thrust that is being shown on screen. Moving on to a fairly powerful engine, we've got the SpaceX Raptor engine. Now this has a unique fuel type, which is methalox. This is methane and liquid oxygen. The reason it's methalox is because the Raptor engine is designed for the Starship missions, and Starship is designed to go to Mars, and it is theorized that methane can be locally produced on Mars, which would obviously fuel these rockets to travel further into space. Now, methalox also offers high TWR and efficiency. The SpaceX Raptor engine is extremely efficient because it uses a closed cycle design, so it runs at a chamber pressure of over 300 atmospheres, and obviously it's got great ISP and thrust figures. Having selected an engine to work with, we now move on to the next hurdle in spaceflight, which is clearing the atmosphere. Earth has a pretty thick atmosphere, and obviously the atmosphere decreases in density as you go further upward. When our rocket's on the ground, the atmospheric density is at a maximum, but our velocity is at a minimum, which is 0. Once we're in space, our velocity is at a maximum, which is orbital velocity, and our atmospheric density is basically 0. But between these two extremes, there comes a point where our velocity is very high, and our atmospheric density is still high, which leads to a maximum pressure area, which is called max Q. Now, this subjects great aerodynamic stress to our spacecraft, and it also wastes a lot of fuel. So the solution to this is obvious. As we're approaching this calculated max Q, we throttle down our engines so that we preserve our velocity and don't over-accelerate, and we clear the dense parts of the atmosphere such that when we go high up enough in the atmosphere, we throttle back up to full power and continue on. Through this, we've saved fuel, we've reduced the aerodynamic stress on our rocket, and we've gotten to space in an efficient manner. Once we cross the 100-kilometer altitude line, we are officially in internationally recognized space. So our aircraft has now become a spacecraft. As we're clearing the atmosphere, we need to keep in mind this one important fact. To achieve orbit, we need to have a very high lateral velocity, which is horizontal velocity. But when we're launching off the launch tower, we're pointing vertical, so we end up getting a high vertical velocity. So we need to efficiently convert this vertical velocity into lateral velocity without reducing the effective thrust that our engine has. So essentially, we're trying to minimize steering loss, right? To minimize steering loss, we perform what is called a gravity turn. So once the rocket has launched, just freshly launched, and has cleared the launch tower, we perform what's called a pitch-over maneuver, where we use the engines, we gimbal the engines, so essentially turn the engines, and force the rocket to turn maybe 5 to 10 to 15 degrees between that range, and then we turn the engines back such that the engines are pointing in the direction of velocity, and we're using 100% of our thrust to move forward. Because we've turned 15 degrees, 10 degrees off the vertical axis, gravity begins to pull down the nose of the spacecraft further and further and further until eventually it will be perfectly horizontal. All this time, the engine is just working to increase our physical speed. Now, this, like I said, minimizes steering losses, but this means that to turn the aircraft 90 degrees, all we had to do was just perform a tiny little pitch-over maneuver right after launch, which means this actual fuel we used to turn was very, very little. With all that done, we have now achieved orbit. And now that we're in orbit, we need to consider the sort of economics of moving around in space and exploring space. This brings us to the sort of currency we can use when we're talking about astrodynamics. This currency is called delta V. Essentially, delta V is the amount of change in velocity that your rocket can produce. Whether it be decreasing your velocity or increasing your velocity, this is just the amount of velocity your rocket can change. You can think of this as the cruising range of your car. Regardless of how powerful your engine is or how big your tank is, ultimately all of those values can be computed or funneled to create the specific value, which is how many kilometers your car can drive. In the case of spaceflight, we don't look at kilometers, we look at kilometers per second. So delta V is the universal currency for space travel. It takes a very specific amount of delta V to get from the surface of Earth to an orbit around Earth. It takes the same amount of delta V to get from the surface of Earth to the moon or beyond. And if a spacecraft runs out of delta V, it's similar to a car running out of fuel, which is you're stuck where you are. You can't make any changes until someone comes and rescues you. Now, delta V can be related to the mass of a rocket using this equation. We've got three unknowns here. Our first unknown is the exhaust velocity of the exhaust coming out of the engine. Our second unknown is the wet mass of the rocket, which is essentially the rocket fully fueled, sitting on the launch pad or sitting in orbit around the Earth. And our final mass is the dry mass, which is the mass of the rocket after all the fuel has been expended and it has no more to give. Now, this mass ratio is locked inside a natural logarithm, which means to double our delta V or double the traveling we can do in space, we need to square the mass of the rocket. Essentially, that means if we were carrying 20 kilograms of propellant, or our rocket weighed 20 kilograms, then we need to add 380 kilograms of propellant on top of that to just travel double the velocity. Now, this results in our rockets being disproportionately weighed, where 85 to 90% of the rocket will just be propellant and only 10 to 15% will be the actual payload you're sending to space. To further maximize delta V, once we're in space, we drop off spent stages and spent engines because, like I mentioned earlier, different engines are useful for different parts of spaceflight. So once we're in orbit around the Earth, we drop off our high TWR, low ISP engines, and we drop off fuel tanks that are emptied just to save us a little bit more mass to gain that extra bit of delta V. This process is called staging, and it's very common everywhere. To show you how drastically we stage a rocket between the surface of the Earth and the Moon, for instance, I've got a little animation for you. So we're starting off on the surface of the Earth. This is the Saturn V rocket in the Apollo 11 mission. We're launching with our Rocketdyne F1 engines, producing insane amounts of thrust and pushing us into orbit. Our core stage continues burning for a few minutes until we've expended that fuel and we jettison that stage. So we have a lot of engines and an entire fuel tank that we've just lost in weight. And then we burn our next stage, which we then spend. And we've got a fairing that also goes. And by now we've already saved a lot in the dry mass of the rocket because we've jettisoned a lot of metal. This stage now continues to burn for another few minutes until we're in orbit, and then it too jettisons, saving us another ton or 2 tons or lots of tons, and we end up with this little contraption which we park in Earth orbit. Now this stage fires its engines to put the capsule on a path to the Moon, and once again, once it's spent its fuel, it is again jettisoned. Now in the case of Apollo, obviously we had the lunar module hiding inside the stage, so once they jettison, it performs a docking maneuver where it then connects and then moves apart. So as you saw, we shed an insane amount of metal and fuel and resources just to get a tiny little capsule on a path to the Moon. Now here are some common delta V figures for different trajectories around the Earth. If we want to be in low Earth orbit, which is roughly 400 kilometers above the Earth's surface, this is where the ISS orbits, we need around 9.5 kilometers per second of delta V. If we want to go into Sun synchronous orbit, also known as polar orbit, where we can see all of the Earth, so usually satellites that are looking down on Earth and surveying the Earth will enter this orbit, we need to enter Sun synchronous orbit, which will require a delta V of 10 kilometers per second. The disparity between these two exists because when we're launching in low Earth orbit that is equatorial, the Earth's rotational momentum, because the Earth rotates, adds onto our rocket's momentum and we get that extra little speed boost, which is worth 500 meters per second. If we're going into Sun synchronous orbit, we need to cancel that out so we can go in a vertical polar orbit around the Earth. There's a bunch of other orbits as well. We've got geostationary orbit, where our orbital period is the same as Earth's rotation, so we get a dead-on view at one specific part of the Earth. That requires 13.5 kilometers per second because we're going much, much higher. And a highly elliptical orbit, depending on how you configure it, where you can have a very, very elongated orbit, or you can have a very, very skewed orbit. Its delta V requirements vary, but the one I've included requires 12 kilometers per second of delta V. Moving on, there's another way we can improve the efficiency of our rocket, and this is to change between sea level and vacuum engines. Now the same engine, the same physical engine with the same fuel type and same combustion chamber can produce different results whether based on the nozzle that you attach to it. So as you can see, I've got 2 types of engines here. I've got the SpaceX Merlin 1D's vacuum level variant and sea level variant. And the reason they're different and the nozzle bells on one is so much larger than the other is because the nozzle bell allows this exhaust gas to expand. Now, on sea level, you have atmospheric pressure to deal with. So you don't want to expand the air too much, otherwise atmospheric pressures will push air into the engine and that will cause the engine to effectively self-destruct. But in a vacuum, you can allow your exhaust gas to expand basically until its density is the same as a vacuum, which is 0. And that affords us a much, much higher compression ratio or expansion ratio. So for a vacuum level engine, our expansion ratio is 165 to 1, but for a sea level variant, we can only afford 16 to 1. And obviously this shows in the ISP figures because a vacuum engine squeezes out a bit more energy as that gas expands, producing a bit more thrust, which leads to us having a better ISP of 348 seconds versus the 311 I showed you earlier. Like I said, you cannot use a vacuum nozzle on Earth in atmospheric pressure, but you can use a sea level engine in space, even though that would technically be operating it inefficiently. So just a quick recap of getting to Earth's orbit. As you can see, we have a rocket here. This is SpaceX's Dragon spacecraft, and it is launching through the atmosphere. It performed its gravity turn. It's now shedding its stages. It's firing its secondary stage, and the core stage will then re-enter the atmosphere and either burn up or land and be reused. As you can see, the burn that injects a craft into orbit, its secondary stage, is quite a longer burn because it's low thrust but high ISP, so to produce the same amount of change in velocity, we need to burn for much longer. As you can see, the core stage is just re-entering the atmosphere now, and from here we will have entered orbit. And that takes us on to the next stage of exploration, which is the next order of magnitude. So we're already in low Earth orbit, but before we even think of venturing into deeper space, we have a few things to consider. Firstly, space is a vacuum, so heat dissipation becomes very, very difficult, and heat extremes exist. So for a spacecraft, the side that faces the sun could be baking at 120 degrees Celsius, but the side that's facing away could be freezing at minus 150 degrees Celsius. This is the same reason planets like Mercury, planets without atmospheres, bake and freeze at the same time. So the common solution would be to insulate the spacecraft, but we can't afford that because we're trying to maximize our payload mass. We don't have a lot of mass to work with, so we don't want to be spending our budget in mass with thick insulation around the spacecraft. Instead, we use something called multi-layered insulation. This looks like a thin gold blanket around the entire spacecraft, and this essentially prevents this extreme disparity in temperatures on different sides of the spacecraft. It also protects the spacecraft's internals so heat doesn't escape. But that obviously creates a secondary problem, which is electronics and heaters and power sources can generate a lot of heat inside the spacecraft, so we want to vent that heat out. To vent that heat out, we can use the Stefan-Boltzmann law, where we radiate the heat, because radiation is the only form of heat rejection available. We can't use convection, we can't use conduction. The mechanism we use is the Stefan-Boltzmann law, and this involves an active thermal control system, which we also call a radiator. This radiator involves pipes where liquid ammonia is pumped through cold plates, and this liquid ammonia obviously redirects heat from heat sources inside the spacecraft to the radiator panels where it is radiated into space as infrared light. A good example of this is the International Space Station, where we've got our solar panels, these big golden plates, but we've also got our radiators, which are white looking plates with the liquid ammonia flowing through them. Now that we've fixed the problem with heat rejection on our spacecraft, we can finally set a course for the moon. To get to the moon, I've compiled a delta V budget required. As I talked about earlier, delta V is the currency we use in astrodynamics when we're traveling in space. Now, to get from Earth to low Earth orbit, we need 9.3 kilometers per second of delta V. To get from Earth to a trajectory that intersects the moon, we need 3.1 kilometers per second. Once we arrive at the moon, to capture in lunar orbit, we need an additional 0.9 kilometers per second. And finally, from orbit, if we want to land on the surface of the moon like the Apollo astronauts did, we need an additional 1.9 kilometers per second of delta V. Now, to actually make sense of these values, of this total 15.2 kilometers per second that we need to make some assumptions. So our first assumption is that the exhaust velocity, essentially the speed at which gas is escaping our rocket engine, is 4.4 kilometers per second. From there, we obtain two values: our mass ratio if we started on the surface of Earth, and our mass ratio if we started in orbit around Earth. If we started on the surface of Earth, we would need 30.6 tons of fuel to send 1 ton of payload to the moon. If we started from Earth orbit, we would only need 2.9 tons of fuel. So that is 10% of the requirement from if we started on Earth. This is because Earth has a very, very deep gravity well, and we want to take advantage of this disparity to be more efficient in the amount of fuel that we're using to get the same amount of delta V. How do we do that? Well, we cheat the rocket equation. So we use something called orbital refueling, because if we want to take any real payloads to the moon or beyond the moon, because we're literally just at the moon so far, using a single launch becomes incredibly inefficient, because just to get enough, to get any usable payload, so labs or bases to the moon, we would require rockets on Earth that are the size of skyscrapers. And factoring in real world losses, as you can see with the red curve, there comes a point where you just can't send any more mass on a single launch to the moon. This asymptotic value is 80 tons, or the equivalent of 5 fully fueled lunar modules. However, there is an option. If we launch 2 rockets, where one rocket launches our payloads, or our bases, our landers, our rovers, but without any fuel, and then we send a second rocket that is just an orbital tanker to refuel all of these rockets, all of these space probes, we end up with a much gentler curve, which is the green curve, which essentially is the required mass on our launch pad, our total mass on the launch pad, to actually get enough delta V to get a specific ton of payload towards the moon. The act of launching 2 rockets resets the rocket equation, because in each launch we need to get much less mass into orbit, and that obviously drastically reduces the requirements for us to launch from Earth. Now there's another problem. Now that we've orbitally refueled our rocket, to actually get fuel to pump from one tanker to our spacecraft, remember we're in zero gravity, so fuel's just going to float around. So in half empty tanks we're going to end up just pumping gas, and that's very, very dangerous, because that will overspeed the pumps, and that will cause the pumps to damage themselves, which will leave you stranded in space. So to actually refuel, we need our fuel to essentially stick to our engines or to the valves. What we do then is we have tiny, tiny rocket thrusters that fire very briefly, and that sort of jolts the fuel inside the liquid fuel and pushes it towards the other end, and that creates a clean liquid transfer between the orbital tanker and our rocket that's headed to the moon. Again, we don't want this engine, this ullage engine, to be too powerful, otherwise we're actually changing the course of our orbit and also expending a bunch of fuel just to transfer more fuel, so that becomes inefficient. Moving on, now that we've got a fully fueled rocket in low Earth orbit, we need to find efficient ways to get to the moon. Now this is where a bit more orbital mechanics related stuff comes in. We're going to talk about 2 specific principles. Well, 2 specific interpretations of one principle, which is the Oberth effect. The Oberth effect essentially is that a rocket can generate a lot more kinetic energy for a given amount of delta V if it was already moving faster. What this means is, well, we can understand this by looking at the equation. You can see the delta V symbol in the first term is multiplied by m times v, which is the momentum. Now if we have a higher momentum, the same amount of delta V will increase our kinetic energy a lot more than if we were at a lower speed, or our V was a much smaller value. How does this translate to orbital mechanics? Well, as you can see, the white orbit was our original orbit. If we burn at periapsis, where we're closer to the Earth and we're moving a lot faster, we generate a lot of extra kinetic energy, which pushes up our orbit a lot higher than before. However, if we fire closer to apoapsis, where we're moving a lot slower, the same delta V doesn't realize a lot of kinetic energy change, and that leads to us having a much smaller orbit or a much smaller change. Conversely, if we want to change the plane of our orbit, plane changes are regarded as very inefficient maneuvers. We want to do this when we're very high up in the orbit, because that will lead to a much higher change, because we're essentially cancelling out our horizontal velocity and introducing vertical velocity so that we can have a more polar orbit. So if we do this when our speed's slower, it will be more efficient than if we did it when we were much closer to the Earth, moving much faster, because then there's a lot more velocity we need to be cancelling out. So the two things to remember is, if we're increasing our kinetic energy and raising our orbit, that is most efficient to do when we're closer to the Earth, but if we're changing the plane of our orbit, that is most efficient to do when we're furthest away. That brings us to the maneuver that actually gets us to the moon. This is the translunar injection. This is essentially a burn you perform in low Earth orbit that puts you on a course that intersects the moon. So, like I said, we need 3.15 kilometers per second of delta V, and that changes our apoapsis, which is the highest point in our orbit, from 200 kilometers to 400,000 kilometers, so that it really elongates our orbit. The timing of this burn is critical because you have to keep in mind that the moon moves really quickly in its orbit, and we also will be moving towards the moon at a slow pace. So we will take 3 days to get to the height of the moon, and the moon in that time will have moved 60 to 70 degrees in its orbit. So we don't want to aim at where the moon is right now. We want to aim at where the moon will be in 72 hours. And obviously the margin of error is very small because the moon is very small and it is very far away. Obviously, I'm sure you've heard of the fact that you could fit all the planets in between the Earth and the moon and still have space left over. That's how far the Earth and the moon are from each other. Now I want to talk about a very specific type of translunar injection, which is a very safe and efficient way to explore the moon. This is the free return trajectory. Essentially, the basis of this trajectory is that it uses the moon's gravity to alter its orbit around Earth such that it will enter the Earth's atmosphere without any further burns or propulsion needed. This is very useful if we're testing new engines, or if our engines are unreliable, or if we need a quick way home. So, for instance, in the Apollo 13 mission, when the service module had a rupture, the astronauts used the lunar module to put the entire system on a trajectory, on a free return trajectory, such that it would slingshot behind the moon and then head straight towards the Earth. This trajectory has also been used by Apollo 8, and much more recently has been used by the Artemis 2 mission. And obviously it has been proven safe and is a great way to test new hardware, new engines, or just get home. Now that we're on a trajectory that intersects the moon in a few days, we have another hazard to worry about. This hazard is invisible. We can't see it with our naked eye. And obviously what I'm talking about is the fact that we're leaving Earth's magnetosphere. The further you get away from the Earth, your shielding reduces, and essentially at one point you cross the boundary and you're in the same amount of, you're getting the same amount of radiation that the moon does. The process of exiting this shield is arguably more dangerous than being in interplanetary space, basking in solar radiation. This is because of two donut-shaped rings around the Earth called the Van Allen belts. And these belts essentially store or trap some of the high energy radiation that comes from the sun or interstellar space and prevents it from hitting the Earth. As we're passing between these, we're exposed to an insane amount of radiation. And obviously the considered solution would be to improve our shielding, and we can do that, but only to a certain limit, because we are still constrained by our delta V budget and our mass budget. So we combine that with speed. Our TLI burn is such that we just punch through the Van Allen belts, and we reduce the time spent in this radiative zone, and that in turn reduces the radiation that we experience, or our astronauts experience. To protect our computers, we use 3 separate CPUs that perform the exact same calculations, and once their calculations are complete, a voting system is essentially done to ensure that if radiation had struck one of the CPUs and changed one of the bits in what is called a single event upset, we aren't losing or performing drastic errors in our calculation, and those errors can be filtered out. And in the background, usually algorithms will scrub through data to make sure any bits that have been flipped by radiation are flipped back through the same voting system. Okay, well, we've protected ourselves from the magnetosphere now. So we move on to a new problem, which is, how do we know where we're going? I'm sure a lot of you have heard about the 3-body problem. And the 3-body problem is essentially an extrapolation of Newton's law of gravitation. Look, gravity has an infinite range, right? As long as you are a distance r away from a body, gravity will act on you. Obviously, it'll become increasingly insignificant the further you get away from it. But as a spacecraft travels through space, it is affected by the Earth, it is affected by the Moon, it is affected by the Sun, it is affected by large planets like Jupiter, and this changed the trajectory of the spacecraft. If we use two-body physics, the solution is very simple. But if we use three-body, it becomes really, really hard to solve, and you essentially have to brute force it. So modern computers choose to brute force it numerically to solve for the trajectory that the spacecraft will probably end up taking. However, back in the day of the Apollo missions, we didn't have the luxury of a lot of compute. So we used what we called the patched conic approximation. This essentially involves us defining a sphere of influence. So the sphere of influence is going to be the point where we say, okay, the moon's gravity is stronger than the Earth's, and we don't even consider the Earth, we just consider the moon. And whilst we're leaving the Earth, whilst the Earth's gravitational force is stronger on the spacecraft, we consider only the Earth and we don't think about the moon. And we then patch these two at the boundary of the sphere of influence, or the SOI, and this is why it's called the patched conics approximation. The reason it's called conics is because these are conical shapes. So the trajectory around the Earth is either parabolic or elliptical, and the trajectory around the moon is hyperbolic. Now, how do we decide where these spheres of influence lie? We have a mathematical way to obtain it. This boundary essentially will just define the difference between the force of gravity and define the point at which one becomes stronger than the other. Now, obviously, both of them are still acting regardless of where you are in between the Earth and the moon. However, this is just a simplified approximation we can apply in a system where we have only three bodies. And as you can see in the equation, the larger value of m, or capital M, is Earth's mass, small m is the moon's mass, and r ends up being the distance at which the SOI boundary lies. And as you can see in the patched conics approximation, the red path is hyperbolic, and the blue path, which I have obviously cut down, is going to be elliptical. The velocity with which we enter a celestial body's SOI, so in this case the moon's SOI, and the velocity we leave it with, is called the hyperbolic excess velocity. So essentially this is the velocity that will exist when you come in and leave because of the conservation of energy. Like I said, gravity is a force that has an infinite range. So even though we're using this patched conics approximation and looking at spheres of influence, in real life, obviously, gravity acts on you even though you are on the surface of Earth. So lunar gravity acts on you, solar gravity acts on you, Jovian gravity acts on you. But because of this, we have interesting geometries where there are certain points in the two-body system that have certain properties, such as no gravitational field, or no net gravitational force. So you can sit or orbit that specific point. Now we call these the Lagrange points. We've got 5 of them, and they exist for every single two-body system. You've got one for the Earth-Sun system, one for the Jovian Sun system, one for the Earth-Lunar system. The first of these points is L1, which is located between these two bodies. So there is a point between Earth and the moon where the Earth's pull on you and the moon's pull on you is equal and opposite, so it cancels out and you can orbit that little point. That's L1. L2 is the point behind the moon. So you are behind the moon such that the Earth's gravity and the moon's gravity pull you towards the center, and that essentially allows you to orbit that specific point. So that's behind the moon. L3 is on the opposite side of the system. So if you were to draw a line from the moon to the Earth and continue that line to the other side of the moon's orbit, that's L3. That's located behind the larger body. And you obviously, because of this geometry, have 2 other points, which is L4 and L5. L4 is 60 degrees ahead of the smaller body, and L5 is 60 degrees behind. So if you look at L3, L4, and L5, they form an equilateral triangle on the circle of orbit of the smaller body. Now, these Lagrange points are very useful for specific missions. For instance, L2 in the Earth-Sun system is where the James Webb Space Telescope is, because the Earth perfectly hides the sun, and the spacecraft can be cooled appropriately to perform the discoveries it does. L4 and L5 are gravity traps. So essentially, you have lots of asteroids and rogue objects just get stuck there in that mini gravity well and just stay there. So Jupiter, being the largest of the planets, has its L4 and L5 traps, and lots of asteroids get stuck there, and they're called the Trojans. Great, so I just want us to quickly review what we've done so far. From low Earth orbit, we looked at the Van Allen belts, we looked at the radiation it causes, then we looked at the Oberth effect and how we can burn very close to the Earth to increase our velocity. We then looked at the fact that it takes 3 days for us to get from the Earth to the Moon, and that the Moon moves, so we need to lead our shots in advance. And we talked about the translunar injection. And because this is Artemis 2, we also talked about the free return trajectory, where no further burns need to be done, and we slingshot around the Moon on a trajectory that takes us straight home. We also talked about the delta V requirements to get to the Moon. And obviously we talked about the Lagrange points that sit in this Earth-Moon system, as well as other two-body systems. Now that we've conquered this area around the Earth, we move on to the next stage of space travel, which is interplanetary travel. So the first step in becoming interplanetary is recognizing that we don't know where up, down, left, and right is anymore. Remember, if we are far away from the Earth, we can't really use Earth as a reference to say, okay, that's up, that's down, that's left, that's right, like we can do on planet Earth. So we define 6 vectors in our space travel that we use for any specific movements regarding the spacecraft. These 6 vectors are prograde, retrograde, radial in and out, and normal and anti-normal. Prograde is you burning in the direction of your travel. So if I wanted to increase my orbit or increase my speed, I would burn prograde. If I wanted to slow down or decrease my speed, I would burn retrograde, which is opposite direction of travel. If I wanted to change my orbital inclination, right? So I talked about plane changes. If you wanted to create a plane change in your orbit, you would burn normal or anti-normal depending on how you want your orbit to tilt. And radial in and radial out are really useless directions to burn in. They just waste fuel because you're not really changing much in your velocity. You're burning normal to the velocity of your spacecraft, and that's just a nice way to burn fuel and lose delta V. A note here is it is very easy in interplanetary travel to accidentally have some part of your velocity be burning, some part of your engine be pointing in the direction of radial in or out, and that obviously reduces the efficiency of the maneuver that you are committing when you are burning. Now, to become interplanetary, we need to consider the fact that we are leaving Earth's sphere of influence, so we need to know what hyperbolic excess velocity we need. So to leave the Earth's SOI to go to Mars, we need a hyperbolic excess velocity of 2.9 kilometers per second, but we need to make sure we point in the direction that Earth is moving, so that Earth's speed around the sun can add to our speed and our orbit can effectively be raised to the height of Mars. Conversely, if we're going to Venus, we need to point in the opposite direction, and we need to leave Earth's SOI with a hyperbolic excess velocity of 2.5 kilometers per second. Now, to get from low Earth orbit to the edge of Earth's SOI, we need 3.2 kilometers per second. So naturally, you would assume to get the total delta V requirement would then be 3.2 plus 2.9 or 2.5, depending on where you're going. So let's assume we're going to Mars. You would assume we would need 2.9 plus 3.2 to get to Mars. However, it is important to note that, again, we are exploiting the effects of the Oberth effect. The Oberth effect effectively reduces our requirement to 3.6 kilometers per second and 1.4 kilometers per second, respectively. So if we were going from Earth orbit to Mars, instead of it taking 6.1 kilometers per second of delta V, would actually only need 3.6. You'd also notice that the Oberth effect doesn't really give us an advantage when we're leaving from the Moon, even though the delta V requirement physically is only 1.4 kilometers per second. That isn't far off the hyperbolic excess velocity we need, because we're moving slow when we're at the height of lunar orbit. Similarly, to get to Venus, instead of your 5.7 kilometers per second required, you'd only need 3.5 kilometers per second. Now, we know what speeds we need to get to these different planets, but where do we point our spacecraft? I vaguely mentioned that we are pointing in the direction of Earth's travel to go to Mars, and the direction of Venus's travel, against Earth's travel to get to Venus. But when do we know to burn? How long do we burn? And how much do we need to lead our shot by to actually get to Mars and avoid overshooting Mars or undershooting Mars? Well, this is where the Hoffman transfer comes in. The Hoffman transfer is the standard form of transfer between two planets that are orbiting the sun. It is the most efficient route you can use, cheapest with delta V. And obviously, like, you cannot use the straight line because these planets are moving around the sun. Now, the Hoffman transfer for transferring between the Earth to Mars requires Mars to be 44 degrees ahead of Earth in its orbit. And if you're going to Venus, you need it to be 54 degrees behind Earth in its orbit. In this animation, you can see the first animation, Earth is launching a spacecraft 44 degrees behind Mars. And that spacecraft takes its time to climb away from the sun and eventually meet Mars 9 months later. And similarly for Venus, we lead our shot such that Venus is 54 degrees behind us, and Venus will then catch up with our spacecraft as it falls towards the sun. Now that we're in interplanetary space, we encounter a new problem. Earlier I talked about the three-body problem and how we can fix it using the patched conics approximation. However, once we leave Earth's sphere of influence, there's a lot of bodies acting on us. There's the Sun, there's Earth, there's Mars, there's Jupiter. There's a lot of bodies acting on us in a significant enough way that you cannot negate their effects. And this leads to the n-body problem, where we do not have any algebraic equation that we can use to perfectly solve for the trajectory or the path that a spacecraft would take on its way to another planet. So obviously modern computers use numerical integration and brute force it. So they will advance the spacecraft's trajectory maybe a second or a millisecond, and then they'll recalculate the force, and then they'll see where the spacecraft will go, and they'll repeat this for the 9-month journey all the way from Earth to Mars. And this takes a lot of time, is very computer intensive, and even though we're doing this at millisecond intervals, we could have very, very, very tiny errors that eventually lead to us missing Mars either by being too early or by being too late, and missing it by thousands of kilometers or hundreds of thousands of kilometers. So what do? Well, we keep recalculating. So obviously to do that, we need to know where we are in space. So that brings up a new problem. We already know the 6 vectors of motion, but how do we know what our location is in space? Obviously you don't have GPS in space to sort of just locate where you are, but we can use some clever techniques. The first one is knowing which direction we're pointing in. So obviously, if you are on Earth and you were in a car, you'd know you're going forward because the trees beside you or the road beside you is moving. But in space, nothing close by is really moving, and you're not feeling the force on you because you're at constant velocity. You're not really accelerating in the direction of your travel. As a result, you can't really determine what your velocity is or will be. Similarly, you need to know where Earth is, where Mars is. So we can use a small camera that points to distant stars, and using preloaded star maps, determine where it's supposed to be and which direction it's supposed to point and which direction it's actually pointing. From there, you can use flywheels that exploit the law of conservation of angular momentum to rotate. So if the flywheel rotates clockwise really quickly, the entire spacecraft will end up rotating counterclockwise, and you could do this along all 3 axes of rotation to basically point your spacecraft with millimeter precision wherever you want it before you perform whatever burn you need to, because obviously you will have some deviation. So in the middle of your trajectory of your path to Mars, you can perform a few correction burns that last only a few seconds because you're only correcting maybe a few kilometers worth of a gap on the scale of millions of kilometers, and that can help you correct the effects of the accuracy errors on your computers and eventually get to Mars. Great. After our 9-month journey, we have now approached another planet, in this case Mars. As we approach the SOI, we obviously want to now enter stable orbit around the planet instead of just flying by, because then what was the point? There's 3 specific ways we can enter orbit around a planet. Well, there's 2, but the second one involves 2 specific methods. The first one is using our engines to slow us down, right? So this is when you get super close to the planet, so in this case Mars, you burn your engines retrograde, which is pointing away from where you're going, and that will slow you down, but that obviously will cost you a lot of fuel. But again, it's very reliable. A lot of spacecraft use this method, but because you need to carry the fuel to physically burn to slow you down, that reduces the mass you can have for your instruments or telescopes or surveyors. But it is really reliable. The second method is a little unorthodox, but a few spacecraft have used this. This is aerobraking. Now, aerobraking can be done in 2 ways. The first way is going to be you enter the atmosphere of Mars, and the aerodynamic drag that we talked about earlier when we were launching our rocket actually acts in your favor and slows you down such that you bleed off all your hyperbolic excess velocity. So if your hyperbolic excess velocity is now less than 0, then you have captured in orbit around the planet. And this will save you around between 1.5 and 3 kilometers per second of delta V, depending on how quickly you approached or what your hyperbolic excess velocity was. The only problem with this method is to completely slow down and capture into orbit, you need to dip into the atmosphere like quite a bit low, and that can be risky because you are going to generate a lot of heat, and you need to really thread the needle here, because if you don't, then if you slow down too much, you will crash into the planet. If you slow down too little, you will fly off into deep space. Obviously, once you have been captured into orbit, at the apoapsis, or at the highest point, you need to do a little burn to make sure you aren't dipping into the atmosphere again, otherwise your orbit will keep reducing. The second method involves us capturing into orbit. So it's a mix of the first 2 methods we talked about. So you'll use a little bit of fuel to capture into a very high orbit. So you'll burn off your hyperbolic excess velocity, but you'll still be moving really quickly. So your orbit will be really high. Then you do multiple passes through the atmosphere such that you bleed off a little bit of speed every single time, and slowly but surely your orbit will be at the height you want it, and then you can perform another burn to raise your periapsis above the atmospheric line. A really good example of a spacecraft that used this is the Mars Reconnaissance Orbiter in 2006, and it saved 450 kilograms of space on board for more scientific instruments instead of fuel using this method. It is a very slow method, and it is very safe because you're not dipping very low into the atmosphere. So the Mars Reconnaissance Orbiter used its solar panels to generate aerodynamic friction, and it took 445 orbits over the span of 5 months to actually reduce its orbital height to the required desired height to survey Mars properly. But as you can see, for an additional 450 kilograms of science equipment, this is very worth the risk. Now let's say we weren't just orbiting the planet, we wanted to land on the planet. Well, I've got a little graph here that visualizes the different descent profiles we can follow if we wanted to enter the Martian atmosphere in this case and land on Mars. So we've got 3 different colors for curves here. Firstly, this is the entry, descent, and landing, or EDL family of curves, specifically for the Curiosity rover, because as your mass changes and as your surface area changes, these curves vary. The blue curves show what happens if you didn't enter the atmosphere low enough to bleed off your hyperbolic excess velocity, or in this case, your orbital velocity, because you need to bleed off all your orbital velocity. And if you don't, you will just climb out of the atmosphere and keep going into space. And that's the blue curves. Now, if you enter the atmosphere too low, you'll either burn up, or you will end up losing too much speed such that you won't hit the target you wanted to, because obviously now you're not landing in a specific you're not just capturing into orbit, you're landing at a very specific point on Mars. Or if you enter too quickly, you won't burn up, but you will sustain a lot of damage because of the insane amounts of G-forces you will experience. Now, in the case of Curiosity with Mars, the sort of angle of approach cannot be steeper than 12 degrees, but it cannot be shallower than 6 degrees, which gives you roughly a 5-degree gap of wiggle room to bleed off 90% of your speed. Now, in this case, we're approaching the planet or the atmosphere with 2.2 kilometers per second, 5.5 kilometers per second of speed at 125 kilometers of altitude. And the green curves would show what will happen if you burnt off 90% of that and safely entered the lower atmosphere. Now, Mars is an interesting case, and this is why I've taken on the example of Mars, because the atmosphere is thick enough for proper aerodynamic effects to take place, but it is not thick enough for you to use a parachute all the way to the ground. So we use a supersonic parachute to slow us down from Mach 2 down to 200 miles per hour, and this parachute has to withstand 289 kilonewtons of force, right? And like I said, the Martian atmosphere is too thin to take this parachute all the way down to the ground. So once you're on the ground, once you're approaching the ground, you're going to abandon your parachute, you abandon your back shell, and your rover sort of powers down using engines and fuel and burns retrograde to slow down all your speed and then drop the rover down and then fly away. And I believe in showing, not telling. So this is what that process looks like. So here is our back shell. We are entering the Martian atmosphere at 5.5 kilometers per second. Our current altitude is 125 kilometers. You can see the thrusters constantly adjusting the trajectory to make sure we can actually land in the crater or in the designated landing zone that NASA has set out. Through this heat shield, we burn off 90% of our velocity, and you can see the G-forces that the rover is subjected to are truly, truly extreme. Once we've slowed down enough, thrusters keep firing to adjust our trajectory, and a parachute will then come out at the speed of Mach 2. This parachute, like I said, sustains a lot of force and slows us down to 200 miles an hour, which is still far too quick to land on the planet. From there, once we've slowed down enough, we will abandon the parachute. We will also abandon our heat shield because we no longer need it, and the rover will actually use its cameras to look down on the ground and see what it needs, or where it is and where it needs to land. From there, we abandon the parachutes, we turn on our engines on the sky crane, and we perform a powered descent onto the Martian surface. And because the sky crane's engines are fairly powerful, we don't want to kick up dust that will damage the rover. So as we approach the ground, we're going to lower the rover by a nylon thread, and essentially the sky crane will hover. So it'll throttle down such that its thrust to weight ratio will be exactly 1. And the rover will be lowered down, and once it's lowered down and the sky crane has detected that it is fully on the ground, the sky crane disconnects and flies away and crashes somewhere else and leaves the rover safely on the ground. Now that's a very interesting way to get to the ground. And like I said, the reason I chose Mars was because you require 2 specific types of landing techniques to get to the ground on Mars. So similar to the moon, you'd need to perform a powered descent, but similar to Venus or similar to Earth, you'd need a parachute to slow you down. Moving on, sometimes your orbital height between 2 planets, let's say you wanted to go to Mercury, or let's say you wanted to go to Jupiter, the difference in your orbital radii are going to be so great that the Hoffman transfer stops becoming the most efficient way to get there. In this case, we introduce what is called the bi-elliptic transfer. So getting to the sun is actually harder than leaving the solar system, because to get to the sun, you need to bleed off all of Earth's excess velocity, which is 30 kilometers per second roughly. So our delta V requirements after leaving Earth's SOI are essentially 30 kilometers per second. Now, for such transfers, we use what is called a bi-elliptic transfer. Instead of lowering our height, we first raise our height, then we go all the way up to, let's say, Jupiter's height. And from there, we perform our second burn, which takes advantage of the orbit effect, and we reduce our periapsis all the way until we're right super close to the sun or to Mercury. Then we wait all the way until we get to Mercury, and then we perform our third burn, which is reducing our apoapsis. So we circularize around the sun at a very close altitude. Now, this transfer is only effective if the difference or in your orbital radii are really large. So the ratio needs to be greater than 11.94 for it to be more efficient than your Hoffman transfer. But even then, you can see the Hoffman transfer still remains relatively efficient. And later in this talk, I will mention way more efficient methods to perform such maneuvers instead of just plain burns. But that brings us to the end of the exploration of the inner solar system. We now move on to the exploration of the outer solar system, which is obviously Jupiter, Saturn, Uranus, and Neptune. So to start our exploration of the outer solar system, the first thing we need to now realize is that we have a new problem, which is our source of power. See, close to Mars's orbit, we had the sun's intensity was high enough for us to actually use solar power as a power source for electronics on the spacecraft. Obviously, if you're closer to Mars, your solar intensity is lower than if you were closer to Earth or Venus or Mercury. However, in the outer solar system, orbits are so far away that solar radiance becomes much, much lower. At Saturn's orbit, you are not even getting 1%. You're getting 0.7% of the amount of radiation you would get on Earth, which means you're only generating 0.7% of the power you generate on Earth, which really makes solar panels obsolete and ineffective for use in any outer solar system mission. This means we have to replace it with a different source of power. And a more commonly used source of power is the radioisotope thermoelectric generator, or the RTG. This essentially harvests the heat from the decay of plutonium-238, and that produces a lot of thermal energy. And then we use a thermocouple to essentially force electrons to flow, because electrons will flow when you connect them from a very warm source to the cold source, which is outer space, and that provides a steady flow of electrons, which provides steady DC voltage for the entire duration of the nuclear fuel's life. And obviously, as the nuclear fuel decays, in accordance to its half-life, that voltage will slowly drop because the amount of thermal energy being generated drops drastically. This is extremely effective for crafts that we're sending to the outer solar system and even interstellar, because A, we don't have to depend on a star, and B, we can use that warmth to actually keep our electronics at an operating temperature instead of them freezing due to the cold of outer space. But the second problem we have to deal with now is we're so far away from Earth that actually sending messages to Earth becomes a problem. So this is the Voyager spacecraft, and you can see the high gain antenna it has mounted to it, which is the main defining feature of the shape of this spacecraft. And in the span of the orbits of the outer planets, it takes hours and sometimes even days for a signal sent from Voyager to travel, or any outer craft to travel to the Earth. And by the time it gets there, it becomes heavily attenuated or loses a lot of its power. If Voyager supplied 20 watts of power to the signal it was sending, by the time it gets to Earth, it will be 10 to the minus 18 watts in power. Not to mention that the Earth is a tiny dot in this entire vastness of space you can send a signal to. So even if you're pointing a slight bit off, you'll end up with the signal completely missing the Earth, and Earth will still be wondering where you are. Now, for us to actually receive these signals, we have two methods. Sometimes we can boost the signal using the deep space network. So instead of sending it to Earth, we send it to another spacecraft that's in between us and the Earth, and they can relay the signal to the Earth, adding more power to it, amplifying it. Or we use the deep space network dishes on the Earth, which are these super cool 70-meter large dishes in California, Spain, and Australia, essentially 120 degrees apart from each other because they want to be facing the spacecraft at all times. And these dishes are super cooled to only a few degrees above zero, such that the ambient heat that generates noise, so essentially just ambient noise, is obsolete because the molecules inside it are physically almost stationary because you've taken almost all of their kinetic/heat energy away from them. This allows us to detect signals that are on the scale of 10 to the minus 18 watts, because if we didn't supercool them, then ambient noise is way, way, way louder and would drown out the signal sent by Voyager. Now, depending on where you are in space, the Deep Space Network's supported bandwidth can be from 10 bits per second, which means it would take hours for a single image or message to come through, to 100 megabits per second, which you would see with data rates from probes around and on Mars and around and on the Moon. Now that we've solved these issues, we return to our classic issue of delta V budgets. So the cost to explore the gas giants varies depending on which gas giant you want to go to. If you want to go to Jupiter, to orbit Jupiter using a Hoffman transfer, you need a total of 11.4 kilometers per second. To get to Saturn, you need 12.7. To get to Uranus, you need 12.4. To get to Neptune, you need 14.7. And to get to Pluto, you need 17.5 kilometers per second of delta V. Now, if we extrapolate that data using the most powerful rockets we have available, we obtain a maximum allowable payload list of what we can send to these gas giants using the most powerful rocket, which is the SLS Block 1B. Now, I want to point out that we can't send anything using the Hoffman transfer. We can't send anything to orbit any of the outer planets using our current technology. And you might be wondering why we don't use aerocapture, because I talked about that in terms of getting into orbit around Mars. But the problem is the gas giants have very violent atmospheres, very unstable atmospheres, very windy atmospheres, very turbulent atmospheres. So having a spacecraft plunge into the upper limits of these atmospheres is a very, very risky move, because we don't understand how that will affect the spacecraft. It might even cause it to completely disintegrate because of the significant amount of G-forces. So aerocapture is not a method we can use. And as you can see, with our current technology, we can send no payload to actually orbit the outer planets. But we already have sent spacecraft to orbit these planets, and this means we broke past that theoretical limit. And I will talk about how we've done that. But just to note how extremely we've broken that theoretical limit. Firstly, we've sent 6 tons to Jupiter orbit. We've sent the Cassini-Huygens probe, which is 5.7 tons, to Saturnian orbit. And we've had the Voyager space probes and New Horizons, which performed flybys of these planets. And New Horizons actually performed a flyby of Pluto. It took 9 years to get there. But how do we perform these maneuvers? Because clearly there's something that has been figured out to get to these planets without expending a lot of delta V or requiring us to carry a lot of fuel or to perform orbital refueling, which is in its own way inefficient, even though it's more efficient than single launch. Well, the trick is gravitational slingshots. So we, again, similar to the gravity turn, we make gravity work for us. And in this case, we use gravity to essentially steal momentum from a planet. So we can, depending on how we fly by a specific planet, we can have its momentum be added to ours, or have part of its momentum be subtracted from ours, to either accelerate our craft, decelerate our craft, or perform a plane change, because like I said, plane changes are also very inefficient. This speed is technically free because even though we're stealing momentum from the planet and conservation of momentum applies, the amount of momentum lost by the planet is so tiny that even NASA just ignores that value and just treats it as a fixed planet that's orbiting the sun. So essentially the speed is free. So this is what a gravity assist looks like if you want to accelerate, decelerate, or change your plane. So firstly, to accelerate, we have to approach behind the body so that its gravity pulls us in the direction of its motion, thereby accelerating us in the direction of its motion. To decelerate, we do the opposite so that it pulls us retrograde. And to change our plane, we approach it either above or beneath so that it just pushes us upward or downward. Now, I'm going to take the example of the Cassini-Huygens probe because this spacecraft did a lot of gravitational assists to actually get up to the orbit of Saturn, and it saved an insane amount of delta V doing so. So I've got a table here that shows us the running delta V balance So you can see from when we separated from our rocket, we started off with 2.4 kilometers per second of delta V. And when we reached Saturn, we ended up with 1.3 kilometers per second of delta V. Now, we spent only just north of 1 kilometers per second of delta V, and this was to do minute course corrections so that we could intersect another planet's SOI again to perform another gravity assist. But in total, with our gravity assist, we saved a lot of delta V. We saved almost 20 kilometers per second of delta V simply by performing a gravity assist by Venus twice, and then by Earth again, and then by Jupiter, and finally by Saturn. And these gravity assists aren't just useless and used simply for accelerating our craft. The spacecraft obviously performs a lot of calibration, a lot of scientific experiments in these environments to help, both calibrate and also learn more, about Venus, about Jupiter as it's flying by. Now, and what do you do with 1.33 kilometers per second of delta V? You do this. This is affectionately known as the ball of yarn, and this is essentially a trace of the entire trajectory Cassini took around Saturn throughout its years at work. I also want to point out that during orbital capture, you don't have to only do a propulsive orbital insertion. You can use the gravity assist. You can use a gravity assist via one of Saturn's moons or Jupiter's moons to actually slow down and then use your engines to make up the rest of the difference to capture into orbit. So obviously, using 1.33 kilometers per second of delta V, Cassini performed all of these, and obviously through all of these, it also used a lot of gravity assists using moons like Titan and Enceladus to change its trajectory, especially in this last bit. Now, another spacecraft that used gravity assists to its advantage were the Voyager probes. So essentially, they took advantage of a 1 in 175 year alignment that allowed the crafts to hop from one planet to another using gravity assist. So it would use Jupiter's gravity to get it to Saturn's orbit, then Saturn's gravity to get it to Uranus's orbit, and Uranus's gravity to get it to Neptune's orbit, and so on and so forth until it left the solar system. And even though they're interstellar, they move through space at 17 kilometers per second, which is a lot of hyperbolic excess velocity to be leaving the sun's sphere of influence with. And gravity assists allowed Voyager to reach Neptune in 12 years, where normally it would have taken 30 if you did a direct Hoffman transfer. So not only do you save delta V, in most cases you also save a lot of time. Obviously, with the case of Cassini, a direct Hoffman transfer, if we had done one, might have been quicker because it was a direct route. But in the case of Voyagers, you can save a lot of time with the gravity assist. Despite the fact that it moves at 17 kilometers per second, it would take 73,000 years for Voyager to reach the nearest star, which just goes to show the insane amounts of distance in interstellar space, because now we're entering interstellar space, which perfectly segues us to the next section of my talk, which is the relativistic void or interstellar space. The first thing we need to do with interstellar space is actually understand the scale at which we are. So that little bubble you see there is actually the sun's entire SOI, and well, the sun's influence in terms of solar wind. So beyond that point, beyond the heliosphere, interstellar wind is more powerful than solar wind. And to really understand the scale, if the Earth and Sun were an inch apart, Pluto would only be 3 feet away, which is quite the distance, but Proxima Centauri, which is the nearest star to the Sun, would be 4.2 miles away. Like I said, the Voyager probes would take 73,000 years to travel the interstellar gap. And human lifespans are obviously not long enough to live 73,000 years. So we can't use these classical methods of propulsion to actually get to other star systems within a human lifespan or within the technological lifespan to make it actually feasible or viable. And the amount of fuel you'd require to get a decent amount of payload or a usable amount of payload interstellar is then again very intense. And because you're interstellar, you can't really use gravity assists, because to get to a star would take you so long that performing a gravity assist really doesn't lend you much advantage. So we've established you'd require a lot of fuel to move interstellar, but there's another threat hiding in the interstellar environment, and that is the interstellar medium. Now, interstellar space isn't empty. Interstellar space is full of gas, it's full of dust, and this is the same gas and dust that eventually leads to stars forming. You can see in the Milky Way, all this red area is interstellar gas, which makes up 99% of the interstellar medium. And now the highlighted regions are interstellar dust, which makes up 1% of the interstellar medium. Now, gas density in interstellar space is nowhere near the density you'd find on Earth. On Earth, the density is 10 to the 19 atoms per cubic centimeter, but in interstellar space, it will be 1 atom per cubic centimeter of space. So obviously, if you're moving at the speed of the Voyager craft, which is 17 kilometers per second, very impressive speed, but the gas density would have no effect on you. But if you are moving at an actual speed, which is a significant percent of the speed of light, which you really need to be moving at if you want to cross the gap between stars in a human lifetime, then this gas essentially becomes a particle accelerator, and it will slam into your craft so hard that it will cause A, ionizing radiation, and B, it'll start shredding your craft. We will talk about ways to mitigate this, whilst we talk about ways to actually travel at significant fractions of the speed of light, but I think we've established that it is very important for us to travel at the speed of light. Now, when I talked about interplanetary travel, I said the most efficient way and the most direct route was, or in most cases, the most direct route without gravity assists, was the Hoffman transfer. Now, in interstellar space, the most direct and quickest route is the Brachistochrone transfer. It's a bit of a mouthful, but it's a bit of a misnomer as well, actually. The Brachistochrone trajectory is used to show 2 points, the fastest way between 2 points, and the actual name for this trajectory, this interstellar trajectory, is the constant acceleration trajectory, the flip and burn trajectory, or the continuous thrust kinematic trajectory. It is mathematically the fastest possible path between two relatively stationary points in space. So we're assuming, if we're looking at Proxima Centauri, for instance, both of these stars are relatively stationary to each other, so their distance isn't increasing or decreasing or moving sideways, Now, the way this trajectory works is, for the first half of your journey, you essentially fire your engines, you put your foot flat out, you're accelerating at a constant acceleration towards Proxima Centauri, so your speeds will quickly build up. And then at the 50% mark, you turn off your engines, you turn your craft around, and you start decelerating. So you're spending 50% of your time accelerating and 50% of your time decelerating at the same acceleration. And that will lend you the quickest possible way to get from from one star to another. Now, this obviously is incredibly inefficient, because now our main constraint isn't delta V, it isn't mass. Our main constraint is time. We want to get across as quick as possible, as opposed to as efficiently as possible. So there is the proper Brachistochrone transfer, where you need engines that can actually sustain burning for hundreds of hours constantly, in fact up to years even constantly, and get you up to a significant fraction of the speed of light, which means the ISP you require, specific impulse you require, drastically increases. Now, a modified version of this trajectory would involve you burning for maybe a smaller portion, so you'd have a cruise phase. So you wouldn't be only accelerating or decelerating. Maybe you would be accelerating for 25% of the journey, cruising for 50%, and then the last 25% you use to decelerate. This obviously can be adjusted based on what speed you want to travel at, what you want your cruising speed to be, and the engines you're using, how quickly can they get you up to that speed. And we will talk about these factors when we talk about the relativity aspect of it. Because now that we are approaching significant fractions of the speed of light, classical physics becomes obsolete, and space and time work together to make sure we don't accidentally accelerate beyond the speed of light, right? They're protecting this cosmic speed limit. So because we're traveling at such a high speed, there is a difference between what we observe as viewers on Earth looking at that spacecraft through our telescopes, and there is a difference in what the craft itself observes as it's traveling through space. So this difference in observation, this disparity, can be quantified by the Lorentz factor. So as you can see, we have a v-square term which squares our actual velocity of the craft, and there's a c-square term which is the speed of light. And this, the way this works essentially is if I'm traveling at 0.9 c, right, 90% of the speed of light, my Lorentz factor effectively evaluates to be 2.29. So for every 1 second I experience on the ship, 2.29 seconds pass on Earth, right? So this is the time dilation you'd see in movies like Interstellar. So instead of our time being equal, time slows down. Similar properties apply to both your momentum and your kinetic energy, and you can see how they are modified. Similarly, now that we're no longer talking about classical physics, we're more in relativistic physics, the mass ratios relation essentially changes from the original rocket equation to the relativistic rocket equation, and you can see that change in expression here. So now instead of being locked inside a natural logarithm, we're locked inside a square root. And earlier I was talking about how the interstellar medium can cause real damage. So 1 gram of interstellar dust colliding with a spacecraft at, say, 93% the speed of light is equivalent to detonating a 36 kiloton nuclear device. So from a kinetic energy point of view, it's like I dropped nuclear warheads onto my spacecraft instead of actually just accelerating up to the speed of light. So a lot of shielding is also required. Now, there's going to be a difference between the frames of reference. This is what the difference is. If I was an observer on Earth, we would look at the left axis on these two axes, and you'd see that from my perspective, the craft isn't speeding up beyond the speed of light. It will approach the speed of light. It will become 99%, then 99.9%, then 99.99%, and it will get closer and closer to the speed of light as it burns, but it won't ever cross the speed of light or even hit the speed of light, right? And radio signals that are sent back will be Doppler shifted, so I will get infrared signals. So not only will the signal's power have depreciated because of the distance it's traveling, it will also shift into different wavelengths, and that makes it even harder to detect. And like I said, for a ship that's cruising at 90% of the speed of light, your Lorentz factor becomes 2.29. So 1 year on the craft becomes 2.29 years on Earth. Now, from the ship's point of view, obviously, again, you will never break the speed of light in any frame of reference ever. But because we are constantly accelerating, we won't feel like our velocity is starting to taper off or plateau. Instead, what will happen is the distance that we see in front of us will start to shrink. We will physically see the star in front of us sort of become closer, such that the actual distance between us and that feels like it's a shorter distance, and that obviously is divided by the Lorentz factor. And our clock will still be ticking normal to Earth time, right? So if from Earth's point of view, we're looking at the ship, you'd think everyone's moving in slow motion. But in reality, on the ship, they don't feel this difference. So instead, the difference is compensated by length in what is called length contraction. So a star that is 10 light years away will feel like it's 4.36 light years away for us, for this example, because you can divide 10 by 2.29 and you get 4.36. And because we're traveling at 90% the speed of light, the distance is 4.3 light years, but it is 4.3 light years. So you divide it by 0.9 to actually get how long it would take us to get it, because for us, we're traveling at 0.9 c. And that would then mean it takes us 4.8 years to get from Earth to this destination. And obviously there's going to be Doppler shifts, so a red star starts appearing purple because it starts getting blue shifted, and the Earth starts appearing purple as well because it's blue that's getting red shifted. And this leads us to a problem, which is the one-way transfer, essentially, because you will be moving at these really quick speeds and you'll get to your destination star really, really quickly, relatively. And despite that, Earth will have experienced a lot longer time delay, which means you will still be young when you get to your destination star, but everyone on Earth will have aged a lot more than you will. And by the time you get back, everyone will have, aged quite a lot, and a lot of technology would have advanced, a lot of changes would have happened. This is the point of view of a spacecraft that is accelerating to interstellar speed. So you can see that blue shift in this cone of stars in front of you, and you can see the stars just whizzing by us. And as we continue to approach, our field of view physically decreases until it becomes this purple blob of just high energy radiation coming to us straight from in front of us in the direction we're traveling, until we start slowing down, and then the blue shift effects return, then the motion blur also subsides, and then blue shift subsides, and we are at a new point in interstellar space. Now, I want to bring in an example of the movie Project Hail Mary, because they used this technique. Grace used this technique in the Hail Mary, this ship, fictional ship that uses fictional propulsive methods, which is astrophage, and it burns on these brachistochrone trajectories to get to the Tau Ceti system. And Project Hail Mary uses a constant acceleration of 1.5 g, and the effective specific impulse of these engines is 30.5 million seconds, compared to the 100 seconds that we get, 100 or so seconds that we get with our engines. This is a huge difference. And the cruising speed of the Hail Mary was 93% of the speed of light. So a 4-year trip for Grace, essentially, to travel those specific light years to get to Tau Ceti, would be a 12-year wait on Earth. So everyone would be waiting for 12 years before Grace got to Tau Ceti, and then obviously there's the research and whatnot he did before he eventually decided to head back, and then we all know how the movie ended. Now, obviously, we don't have astrophage in this universe, so what do we do? Well, in the 1970s, there was a very rigorously engineered blueprint that was set forth for a torch ship. We call spacecraft that like to burn for very, very long torch ships because they're essentially just torches that are ships. And it relies on what is called inertial confinement fusion, and it accelerates up to only 12% of the speed of light. Compared to the spacecraft we talked about, that is close to nothing, even though 12% of the speed of light is an insane amount of momentum. Now, this requires us to have 50,000 tons of fuel, right? 50,000 tons of fuel to accelerate and cruise and then fly by our destination. We still wouldn't be able to stop. To stop, we would need even more fuel. We need 50,000 tons of fuel. And what makes this worse is the fuel we need is very rare on Earth. It's heavy hydrogen and helium-3. So we'd need specific types of engines. So because we're burning for so long, we don't want our engines to melt. So we use magnetic engines, magnetic nozzles. So once the combustion has happened, the exhaust flows out, and superconducting magnets redirect this exhaust, because this exhaust is magnetically active, and it pushes it out the back in a very specific direction to effectively generate thrust. And this magnetic nozzle will be dealing with temperatures or plasma that is at temperatures of 100 million degrees. So you can obviously understand why we're not letting it physically touch the nozzle. And the fuel requirements are insane, the temperature requirements are insane, and all of that only for 12% of the speed of light, and you end up with a flyby and you can't even stop at your destination, leads to, well, a project that really never happened, obviously. Now, the other way to do this, because inertial confinement engines, fusion engines, have a mass to energy conversion of only 1%, roughly 1%, we can use antimatter. Antimatter catalysis, as you know, if you slam a positron and an electron together, both of their equivalent mass will be converted into pure energy, 100% pure energy, and that leads to us getting much better energy density for the fuel we're using. So we won't really need 50,000 tons of fuel. The problem though here is photons aren't magnetically active, so you won't be able to channel that exhaust gas properly. So the solution is, instead of using electrons and positrons, use protons and antiprotons. So they're much heavier, and the resultant from the combustion will be specific particles. So the particle in question would be a pion. So it's called a pion drive because you will obtain these subatomic particles that have a positive pi charge and a negative pi charge, and because they're electrically charged for these are electrically charged particles. The magnetic nozzle can effectively act on it and push it in one specific direction. And these particles are not long-lived. They really quickly decay into photons, which is gamma radiation. But for the split second, or for the minute duration of time that they are, the magnetic nozzle can quickly get to work and shape them so that then it's just photons coming out the back of the exhaust of the engine. This is what a magnetic nozzle looks like. Obviously, there's a lot of empty space around it. It's not really closed off like you'd expect a normal nozzle to be, but that's because it really doesn't need to be. All you need is just magnets to point the exhaust, and nothing else will happen. In the event that you didn't use magnetic exhaust, the 100 million degrees of Project Daedalus would have melted the engine, would have melted the fuel, it would have completely ruptured your spacecraft. And the delta V potential for the pion drive is essentially limitless, because any mass you can pack on in terms of antimatter is just pure propellant. The only thing you need to be careful of is this propellant needs to be magnetically suspended in your tank. Remember, it can't touch the walls of your tank, because then it would combust immediately and lead to complete destruction of the spacecraft. Now, all these unreliable methods involve us pushing a decent amount of mass, so space bases, interstellar spacecraft with gravity rings, with crew on board to other star systems. But let's say we just wanted an observer there, we just wanted to send a computer there, because computers can be much lighter. You can have a tiny chip with a power supply, with a camera, with any other important stuff like a transmitter, and that can weigh much less than any life support system and crew that you would have to send. And now that we've reduced our mass, obviously it will be easier to push it to a certain fraction of the speed of light. But the question is, how will you propel it? Because you only have a transmitter, power supply, and a microscopic camera. The solution is you leave the engine on Earth. So you'll have a laser, a 100 gigawatt laser that shines directly at these sails, these very thin, very, very wide sails that essentially reflect all of the light and that pushes it forward. So the momentum of the light is transferred into this. And if you've shown a 100 gigawatt laser pulse at these sails, theoretically, for a period of 10 minutes, you'd accelerate each of these up to 20% the speed of light, and they would experience a force of 10,000 G. So obviously if somehow we managed to get crew in this method of propulsion, that would be instant annihilation of crew. And with 20% of the speed of light, you'd be able to cruise and fly by Alpha Centauri in 20 years. The problem is, obviously, these are thin sails, and interstellar dust that I mentioned could easily rupture them. So the key is volume. So you send a lot of these, not just one. So you have your 100 gigawatt laser pointing at one, and then you point it at the second, and then so on and so forth, until you've sent maybe hundreds on their way to another star system. The second solution is to have a small magnetic field be induced inside the power supply. Obviously, this increases the amount of power you would need on hand, but then by generating this magnetic field, you can essentially deflect most of the interstellar radiation that would try damage your spacecraft. Now, we've explored interstellar space in theory. We've seen the physics required to explore space. Interstellar space. We've looked at the techniques that can possibly allow us to do it. And now we move on to the ultimate limit, which is intergalactic space. We're going to be talking hundreds of millions of light years. We're going to really be pushing all the way until the very, very edge of what we theoretically can go. See, traveling at 99% of the speed of light will quickly get us into any given part of our galaxy, of the Milky Way galaxy, within a human lifetime. Obviously, you will not have a civilization to send data back to, because this is hundreds of light years we're talking about. So what's the solution? So we all know about wormholes. So essentially, it has been theorized through Einstein and Rosen bridges that it's essentially a shortcut. The classic thing of folding a paper and saying the shortest 2 points is just by pushing a pencil through, putting a hole in it. And this has been theorized, right? But this has its own problems. See, a wormhole is inherently unstable. So even though we'd be speeding up our trip by a lot, and maybe not even have to use relativistic travel. We would the wormhole's very unstable, such that its throat would be crushed quicker than even a photon can get across. So obviously, a photon is the ultimate speed limit. If a photon can't get across, you can't send anything across it, in theory. But to keep it open, you can just force it to stay open. Now, to force it to stay open, you need a force that counteracts gravity, and that's anti-gravity. This does not exist in the observable universe. We haven't observed it yet. And if you can apply this anti-gravitational force using negative matter with negative mass, then the wormhole will stay open, and you can have light pass through. You can have whatever you want pass through at whatever speed you want it to pass through. As you can see, the green particle makes it to our destination way quicker than the red particle, simply because of the wormhole. Now, when I talk about wormholes, you might think of a very popular movie, which is Interstellar, because a wormhole was placed near Saturn. And the reason the film creators placed it near Saturn is because if they placed it near the inner planets, it would have disturbed the orbits of them, because a wormhole ultimately also has its own gravitational well, technically. Now, if we were to take our paper example, and the example in the past slide, on 2D space-time, a hole looks like a circle, which means in 3D space-time, with time being the fourth dimension, our hole or wormhole would look like a sphere, a perfect sphere. So in Interstellar, they showed a perfectly crystal sphere that was 2 kilometers wide, and the edges of the sphere, through the edges of the sphere, you could see light coming in from the other side of the wormhole. And this wormhole, specifically designed by Kip Thorne, an astrophysicist, was designed specifically such that it has a shallow gradient, because when we talk about black holes and areas with such steep gradients, we often talk about spaghettification, where you'd be stretched out, right? But this specific wormhole was designed such that the spacecraft wouldn't be stretched out as it passes through, and it can smoothly and safely pass through it classical speeds, which is the speeds used by Endeavour. Now, we can use wormholes. Let's say we found a wormhole that theoretically takes us wherever we want to go. How far can we travel at an absolute limit? Now, up till now, we've been talking about moving mass through space. But what we're not considering is that space-time also moves. Space-time expands, right? And space-time expands Hubble showed that space-time expands the further it is away from us. So there comes a point, or there is a radius around us, where space-time is pulling away faster than the speed of light, right? And this is called the cosmological event horizon. So to travel beyond this horizon, we can't use any form of kinetic propulsion. We can't use brachistochrone trajectories. We can't use Hoffman transfers. We couldn't use Hoffman transfers for a while now. But we need to stop moving mass through space, and we need to start essentially riding these expansions of space-time, or moving space-time itself to actually move forward, because to get beyond this cosmological event horizon, we need to travel faster than light. We have no other option. What does that look like? Well, in 1994, the Alcubierre drive, the Alcubierre metric, was essentially theorized. And this essentially is a fun way to surf the intergalactic expanse. The way you do this is you generate a bubble around you, and in this bubble, space-time is flat, and you are relatively stationary. So you do not experience any effects of time dilation, regardless of what's going on outside the bubble, because inside this little bubble, you are safe. Now, in front of this bubble, millions of kilometers of space-time is scrunched up into a few meters or a few millimeters, a very small distance. And behind you, space-time is expanded just as violently as it is compressed in front of you. Now, what this does is essentially forces space-time behind you to push you forward, as you can see here, and space-time in front of you to pull you inward. Now, as that happens, the bubble moves forward, and eventually you can move faster than the speed of light without you physically moving faster than the speed of light, because you're bending space-time such that you move quicker. And because you're stationary inside your bubble, you are safe from the effects of time dilation. So through this method, even if you're traveling faster than light, whilst you are moving, you're aging at 1 year per year. As 1 year passes on your ship, 1 year passes on Earth. Now, this is genuinely just a method of surfing space-time, but it has its own constraints. Now, to actually experience this form of transport, intergalactic transport, you need anti-gravity, like I mentioned with Einstein-Rosen bridges, to actually expand space behind you, because you can see it's not a well, it's more of a hill. So you need negative energy, you need negative mass to create that, and we have observed negative energy. We haven't observed negative mass. We have observed negative energy in what is known as the Casimir effect, but we've only observed that on a quantum scale. And here we would need the same amount of energy as if you converted the mass of Voyager, the entire Voyager space probes, to just pure energy, right? And the other problem with this form of transport is that as the bubble travels through space, that little well in front of you is going to trap a lot of radiation. It's going to trap all of the interstellar medium that's in front of it, right? It's like I'm driving with a little bucket and I'm picking up everything that's on the road as I'm going forward. What this means is when I eventually reach my destination and I turn off the warp drive, that bubble is removed. Everything that I've trapped is instantly released forward because of the inertia it has, and it is blasted at my destination planet, destination star, and it carries enough energy now to destroy the planet, completely vaporize the star system. So even though this method will let us travel faster than light, when we eventually reach our destination, we've destroyed everything that we came to see. So this obviously is not possible. And now that we've surpassed all of these methods of travel, we've really reached the extremes of all the theory we have to offer. I wanted to just retrospectively look back at Earth. For the last hour, we've scaled up by massive orders of magnitude. We went from the launch pad to gas giants to near light speed to literally folding the four-dimensional fabric of the universe. But before we wrap up, I want to direct your attention to this image, which is the pale blue dot image. It's the furthest image ever taken of planet Earth. It was taken beyond Neptune's orbit, from 4 billion miles away. And when you look at theoretical physics like Alcubierre drives and exotic matter, it's very easy to sort of get this sense that we are the masters of the cosmos. But we really aren't. We are all together on this one tiny fraction of a pixel, right? That is the true magic of astrodynamics. The universe is hostile. It is huge. But it is very, very beautiful. It is a boundless puzzle. It gives us a ton of rules to abide by, but it also gives us ways to bend them to our will and travel the expanse of the universe. Every astronomical constraint is just a stepping stone for the next generation of engineers and scientists and astronomers to conquer. We have a beautiful, boundless frontier ahead of us, and we are just getting started on our destiny as an interplanetary, interstellar, and then eventually intergalactic species. There is a lot of time before the first human steps on Mars, but there is no shadow of a doubt in the fact that humanity is capable of it. With that, I thank you for listening to me, and I would now field any questions.